Okay, so the next talk's on optimal reads from consistency checking for C++ style memory models, and Hünkar is going to give a talk, and he's looking for internships.
Thank you for the introduction. So in this work, we study a problem called reads from consistency checking, and I will start with an example which builds some intuition on this problem. So here we have a program which contains two threads and two shared variables, x and y, and both of these variables are initially set to 0. And in this program, thread 1 first writes 1 to x and loads y, and thread 2 writes 1 to y and loads x. And we are asked if, under the stochastic consistency semantics, whether these load operations on x and y can both read from the initialization rights. So this is not possible under stochastic consistency, as either thread 1 or thread 2 should execute its first instruction, and after that point, at least one of these load operations can no longer observe the initialization right. However, if you look at the second scenario and ask whether these load operations on x and y can both read from the store operation that is performed in the other thread, then this would be possible. So how can we formally argue that these load operations in the first scenario can't read from the specified writes, but in the second scenario, this was possible? So essentially, the formalization of this problem is called the reads from consistency checking. So in a high level, reads from consistency checking is a fundamental problem associated with a memory model. So the input to this problem is a memory model and an execution for which we only have some partial information about, such as we know where each load is getting its value from, but we lack certain other information about the program. And the task is to check whether this given execution can be consistent in the given memory model. And why do we care about this problem? Because it has some important applications in the context of model checking, testing, as well as some other domains. And this problem has been well studied for traditional memory models, such as stochastic consistency and x86 TSO. However, it hasn't been studied thoroughly in the context of the C11 memory model, and our work fills this gap. So in this work, we study reads from consistency checking in the various variants of the C11 memory model, and our results include efficient algorithms for certain variants and fine-grained optimality results. And we also showed that the problem is NP-hard for certain variants. And on the more practical side, we showed that we implement some of our algorithms, and we show that our new algorithms have an impact in practice. So I would like to first briefly talk about the C11 memory model. So C11 is the underlying memory model behind C and C++ programming languages. And these languages have support for low-level atomic operations, which are load, store, and what's called a read, modify, write, or RW. And the purpose of these atomics is to enable communication between threads. And an important component of these atomic operations is their memory access level. So each atomic operation has an associated memory access level, and different memory access levels have different synchronization and costs associated with them. So, and the available memory access levels are shown as on the right. And for instance, here, stochastic consistency offers the highest synchronization guarantees, but it is the most costly one. Whereas relaxed offers the least guarantees, but is the cheapest one, and so on. And here we also have some real code snippet that shows how these atomics can be used in practice. So in C11, the semantics of a program can be defined as a set of consistent executions. And each execution can be represented as a graph. So on the left, we have a program, and on the right, we have this program's execution graph. So the nodes in this graph correspond to the instructions in the program, and edges represent certain relations among these instructions. And we have three standard relations that can be formed among these instructions. So the first one is program order, or PO, which relates to events of the same thread. And the second one is the reads from, or the RF, which relates the writes to loads, which take its value from. And lastly, modification order, or MO. And this is a total order on the write operations on the same location, and this simply captures the cache coherence. So once we have these relations, a memory model is essentially defined by imposing certain restrictions on how these execution graphs can be formed. So for example, if we consider a memory model M1, which restricts that the union of PO and MO relations should be acyclic, then in this given execution, this execution will be consistent under M1 because there is no cycle that involves PO and MO edges. However, if we consider this memory model M2, which is as an additional condition that the union of PO and RF relations should be acyclic, then this execution would no longer be consistent under M2 as there's a cycle that involves PO and RFHs. So now we have all the ingredients to define the reads from consistency checking problem more precisely. So the input to this problem is a partial execution X and a memory model M, where this partial execution contains the PO and RF relations, but it lacks the MO relation. And the task is to check whether we can extend X to a complete execution that is consistent under the given memory model. And this involves finding an MO relation that turns X consistent in M. So one of the memory models that we consider in our work is called RC20. So this model captures a rich fragment of C11, and it contains release, acquire, and relaxed access modes, but it lacks sequentially consistent accesses. And previously, performing reads from consistency checking on this type of model has been identified as a bottleneck, for instance, in tasks such as model checking. And previous works have a high polynomial complexity for performing reads from consistency checking, such as they either have a cubic or quadratic dependence on the number of events in the execution. And in this work, we show that we can solve this problem in O of n times k time, where n is the number of events and k is the number of threads. So one important thing to point out here is that the number of events is typically significantly larger than the number of threads. So having only linear dependence on the number of events is important. And our key technical contribution to achieve this bound is the notion of minimal coherence witness relation. So I will first discuss the notion of witness relation, then I will discuss the notion of minimal coherence witness relation. So witness relation essentially serves as a witness for consistency. So recall that the task in reads from consistency checking was to find an MO relation that turns the given partial execution consistent, where MO is a total order on the same location rights. However, in witness relation, one aims to construct a partially ordered MO, which only contains the necessary orderings that are implied by the given memory model. And once we have this partially ordered MO that contains the necessary orderings, a witness relation should satisfy that it can always be extendable to a total MO that is consistent under the given memory model. So let me give an example that demonstrates this concept. So here we have an execution which contains the RF and PO relations. And for instance, the RC20 model enforces that the W2 is MO ordered before W1 due to how these PO and RF relations are formed. However, we don't need to relate W3 with any of the other bytes, so it can be left unordered. So this partial MO that we constructed can serve as our witness relation. We don't need to explicitly compute a total MO, we just need to know that we can always construct one, given a witness relation. So in this particular example, we can easily extend this partial MO to a total MO, for instance, by ordering W3 before W2. And there can be multiple ways of achieving this total order. So one of the main contributions of this work is the notion of minimal coherence witness relation. And a key difference between minimal coherence and prior witness relations is that minimal coherence is weaker than prior witness relations. And this allows us to devise efficient algorithms for checking consistency in the RC20 model. So let me give an example that demonstrates the difference between minimal coherence and prior witness relations. So here we again have an execution which contains the PO and RF relations, and a witness relation based on minimal coherence is shown on the left. Whereas in the case of prior witness relations, the resulting witness relation would be something like this. So prior witness relations typically result in stronger partial modification orders, and they add more explicit emojis. Whereas minimal coherence is weaker, and it is more easier to compute. We performed an experimental evaluation of our proposed algorithm in the RC20 and the popular release acquire of the array fragments. So array is a fragment of RC20, therefore it also admits the same bound. And in our evaluation, we focused on two settings, namely model checking and testing. And we took the state-of-the-art techniques in this context, and we only replaced the reads from consistency checking components of them. And then we performed a comparison with the original version. So in the case of model checking, we implemented minimal coherence inside the model checker called TNMC. And in this setting, we let both the original TNMC and our new version of TNMC run for 2 hours per benchmark, and then we measured two metrics. So the first metric is the average time spent per execution, and we also measured the total number of executions explored. And the summary of the results are shown in this table. So we can see that our new algorithm was able to provide significant improvements with respect to both of these metrics. And in the case of testing, we implemented minimal coherence inside a testing tool called C11 tester. And one difference here is that this setting corresponds to the online version of the problem, where the set of events on which the consistency problem is solved is being extended continuously. And we implemented an algorithm based on minimum coherence that is suitable for the setting, but this algorithm does not guarantee the O of n times k bound. And we compared with the original C11 tester, where we measured the total analysis time. And the summary of the results are again shown in this table. You can see that in this setting as well, our new algorithm was able to provide significant improvements. And that was it about the RC20. And I will not discuss all the models that we considered in our work in detail, but I will just show a summary. So we also considered a model called strong release required, or SRA, and we show that the consistency problem is NP-hardness model. And similar to RC20, we showed that the model's weak release required, or WRA, or the SRA model that is free of the RMW operations also admit an O of n times k time algorithm. And we also considered a relaxed model where all accesses are in a relaxed mode, and we showed that this model admits a truly linear time algorithm. And lastly, for the RMW-free fragments of RA, SRA, and WRA, we established that we have a superlinear lower bound. And this result is obtained with respect to the Boolean matrix multiplication hypothesis. And this implies that improving our O of n times k bond is highly non-trivial. So in conclusion, in this work, we addressed the risk from consistency checking problem in various variants of the C11 memory model. We devised efficient algorithms, and we established fine-grained complexity results, and our experimental evaluation shows the impact of our new algorithms. Thank you.
I guess I don't need to introduce myself anymore. I presume the letter R at the front stands for the suspicious requirement that PO union RF is acyclic. Is that correct?
Can you repeat the question again, sorry?
That when you write RC20, the R means PO union RF is acyclic.
RC20 is like a repaired C11.
Say again?
Repaired C11 model.
Okay, so how much of your algorithm depends on the fact that PO union RF is acyclic? Or put another way, how much does this generalize to the full C11 model or something like that?
Yeah, I think it depends heavily on the fact that it's PORF is acyclic.
Okay, thank you.
I have a question. So in your analysis, you've got SRA, various ones. So the stronger models that seem, in some sense, easier to think about are more expensive to do for reasoning. Do you have a sort of intuition for why it's kind of the opposite way to, I would naturally think?
I guess since we are searching for consistency, it's more difficult to find consistent execution if the model is too restrictive, sort of. I think that's my intuition, at least.
Hi, Andreas, University of Edinburgh. So I was curious about that you mentioned that you're not modeling SC in this C20 part. Is that just because that was not that relevant, or is that crucial also that you don't have SC accesses for your algorithm?
Yes, it is also crucial that we don't have SC accesses, because once we include the SC accesses, then the problem becomes NP-hard immediately.
Okay, thanks.
So, Vijay Nagarajan, University of Edinburgh, just following up on this question. It's interesting to me that the read modifier rights often have the same power for synchronization as SC, but you are able to handle read modifier rights, right? Is that right?
Yes.
So I've one more question, and then we'll let you get down. So can sort of the technique you've built here for getting the efficient MO, could that be used on other memory models that aren't C, so like Power or ARM or something? Could you apply this technique to another memory model?
I'm not sure. I guess maybe the basic ideas can be used, but I don't know the details of those models to exactly say if they can be used exactly.
Okay. If there are no more questions, then let's thank the speaker.
Yeah.